My name is Matt Fiddler, and I'd like to talk about the integration between the open source packages we talked about today, xgxr, nlmixr, and ggPMX. So right here, we're going to go through an Markdown document where we've cached everything and actually run everything, so we can just talk through these pieces. Here we have the cache directory we have and the knitting options. The first thing we do is load all these packages, nlmixr, xgxr, readr, dplyr, and xgx. We get of course, these information that all these things have been loaded and they're masking a couple of things. The first part we want to do is load a data set from xgxr. The data set we load is this case 1 PKPD. And then we look at this information to try to figure out what we can figure out about the data. In this case, we arrange by the dose and look at the actual treatments and create the data set here. This is all on the XGX website, and we're basically just recreating this data set from the XGX website, looking at the first cycle of treatment. We're also going to be looking at plotting some of these things. Some of the things that are really useful in plotting in XGX are this XGX theme set, which will use basically a black and white color scheme and other best practices that are found in XGXR. We'll use geom-ci, which helps create the confidence interval and mean plots in a very simple interface. We'll use the XGX scale log 10 in the Y direction, so we can have semi-log plots. What's really nice about that is it has a semi-log grid line, so you can immediately tell by looking at it it's a semi-log plot. The other thing that's really nice about XGX is it has this X time unit scale where you can scale by time, say hours or minutes, which makes more sense than the defaults. Things are done by tens in the typical plot, but you might want it done by hours, so you say every 24 hours or maybe every 30 days or any of those sorts of things. XGX takes care of that by allowing you to change the time units and put the time units into an appropriate place. The other thing that is often useful for pharmacometrics and other types of drug development is we want to make sure people don't take the initial plots we make as the final plots until we have somebody validate what we're doing. So what we have here is this annotation status that tells us if this is a draft or not draft plot. This is what we're using here. XGX theme set. Then with the templates that they have in XGX, we have these types of things set up for us. We have this status is draft, and then we put in the time units and just basically fill out all this information here and start looking at the template plot that is in the XGX website. In this case, we're looking at the data, and then we're looking at it based on the dose and trying to see what happens in that, looking at semi-log scale with the correct units here. And as we evaluate this, we get this plot where we look at the dose based and stratified based on 3 milligrams, 10 milligrams, 30 milligrams, 100 milligrams, and 300 milligrams. You can see it seems to be scaling up with the dose, and the highest, of course, has the highest concentration. It looks sort of dose linear. There's some data missing here, so there's probably some censoring from this particular data set. The next thing you can do is facet based on the dose. That's really done by this facet grid here. And with that, you can look at the individual PK, join them by line, and add this mean plot so you can see the differences between each group's mean and the individuals within it. As well as, in this case, we're looking at the censoring column. This is set up using the same style of censoring that's supported in Monolix. So we have the censoring column inside the data set. And we use that censoring column to put some stars on your plots. And these stars will show where the censoring is located within the PK data. So you can see here there's a lot of censoring in this 3 milligram dose. There's some censoring in the 10, 30, 100, and there's even some in the 300. This censoring occurs when you're below this threshold. So this is basically all of the concentrations that are below the limit of quantitation. It also looks to me, if you look at the variability here, that the variability is pretty low here. It's substantially bigger here, and it keeps on getting bigger as you get higher and higher your dosing concentrations. So it seems like if you look at the variability of what's happening in these concentration data, as you have a higher dose, you have a larger range of concentrations that are observed. Next thing we might want to know is how proportional the doses are. One way to do that, and it's typically the way I do it, is you take that concentration and you divide by the dose and overlay the plots. If we do that, we can see that the plots seem to be on top of each other, implying dose proportionality, with the exception of this piece here. And you can, if you notice carefully, there's not really these confidence bars here on these plots here, meaning there's not very much information. What really happened is these values are probably limited of quantitation, and this is all censoring. So if we take out that censoring, which is easy enough to do, we just filter it so that the censoring is not there. You can see that this cleans up the data very nicely, and you can see that there's a high probability that these are dose proportional. Again, this is probably different because there's a lot of censored information. A lot of data is below the limit of quantitation. Very little is actually above the limit of quantitation. So the next thing we might want to do is explore covariates. We'll just have a really quick example of doing that, the same one that's in the XGX website. Look at the weight and say if it's above a threshold, this weight baseline is above, say 100 kilos, and basically below 100 kilos, and see if anything happens here. For me, if I look at it, I don't see any differences between the high weight and the lower weight categories. They're on top of each other for any of these particular dose groups. So from the exploratory analysis we just ran through, the doses seem to be proportional. The PK seems to have a two-compartmental model, but it's something that you can see here by the two phases of this particular PK. It's actually throughout, so you can see it there. And censoring seems to have a very large effect on the PK data. So next thing we do is we fit the data with nlmixr. The first thing we do is just make it so it's an nlmixr type of data set. So we change the LIDV to DV, similar to what you would have in NOMM. You filter the compartment to just the dosing and the observations. And for now, we actually are going to filter to the data that aren't censored. The next release of nlmixr will support censoring, but for this example, we're just going to show it without censoring. And we'll make sure that we don't have placebo in our data set. So we'll just define this nlmixr model. Again, we're putting these initial estimates for the two-compartment model. And then we have this between subject variability for all the parameters. And the first one I'm going to try is a log normal standard deviation here being estimated. The reason why I do that is because the larger variability as it goes forward, and we'll try that. And we'll check it. And if we check it, we can see initial values that are given here. Again, they're actually based on these initial values here. They seem to be very long because we have this log here. So we see the initial values and what they actually are. Then we have the omega matrix, and we have a little check to make sure we're mu referencing everything. This LKA is with the eta Ka. So the mu referencing seems to be correct, and the model seems to be set up correctly. So first, we'll try the log normal distribution here and fit it. The thing that we'll try next is the proportional. If you look here at this line, we have the update where we have the line right here is going to change from log normal to proportional. So with this update, you can change little pieces of your model to add pieces to it or remove pieces from it. In this case, we're changing the linear compartment model to proportional. And then once we do that, we can estimate with SAM, and we can also try additive plus proportional. So once we do that, we may want to compare all the models. If we compare the models, we can use the Hux table package to compare. The reason why you choose that is there's a Hux reg that will compare models for any type of room compatible model. And in this case, you can see that the nlmixr models are compatible, and you can actually use this information to look at the estimates numerically and compare the three side by side for each of the parameters. And we can also see that it shows the estimates for log normal standard deviation, proportional standard deviation, and the additive plus proportional. Compared to the other, proportional seems to be a little bit better than the additive plus proportional. If you look at the objective functions here, I would say that the proportional and the log normal have pretty good objective functions. Both of them are negative. Proportional is slightly better than log normal in this case because it has a smaller AIC. You can also compare the parameter estimates. If you look at the parameter estimates for the PK parameters, they're very similar between the log normal and the proportional values. In fact, not only for the population values, but for the standard deviations of the between subject variabilities are very similar. Because of that, we'll just choose one of these to do a ggPMX diagnostic. So the first thing we do is we use PMX, nlmixr, and the model we're going to look at, and we'll add some information about categorical and continuous covariates. In this case, we're adding continuous covariates of weight. Look at that, and then we're using the categorical covariate of their treatment. Once we do that, we can add a couple of plots to this controller. In this case, we're going to look at the MPDE versus PRED, and then look at the time varying MPDE and basic plots like dv/ipred, dv/pred, and absolute value of IRES versus IPRED, individual plots, IRES, density plots, QQ plots, VPCs, and VPCs on linear scale. Once that's done, we can look through each of these. This MPDE versus PRED, we can look at the NPE versus time, and all of these standard goodness of fit plots with the model to see how we're doing. It seems that in this particular case, we're fitting the data appropriately. It seems that the PK for individuals, there seems to be a large amount of shrinkage here, so we may want to drop that. VPC shows pretty good fits with mean value going through the center and the 5th and 95th covering the range of variability. And this is also true when you're looking at the normal scale. When you look at these shrinkage, you can see that the empirical Bayesian estimates seem to be okay with the exception of this volume, which we already observed. And you can look at that also if we look at the eta histograms, or we look at this eta matrix plot. So you can see the distributions seem to be mostly normal. The values here are not really that correlated. So the only one that's problematic is this phi, which has a high value of shrinkage. Once this is done, this last thing that's there will create a PMX report for this controller, and it has a default R markdown, which you can change. And this would be giving a report here. And if you give the report, if you select everything and then you update the fields, if there's not a table of contents already there, it will update the table of contents to show you what is in each of the sections of your report here, like this MPDE versus PRED or this MPDE versus time. And these sorts of things are right in Word, so it's easy to cut and paste into the correct, say, report that you're generating. So the last thing we'll really briefly cover is a what-if scenario. What if we're going to try something else? So in this case, we're going to look at a what-if scenario, like what if we're looking at a steady-state dose of, say, every 8 hours? What would the concentrations look like? It's not something we actually looked at in the study, but we could actually simulate to figure this question out. So the first thing we do is create this event table with a 100 milligram dose and every 8-hour dosing at steady state. So say is equal to 1. We add the sampling and then we can print out this event table. What we do next is we set the seed and simulate what would happen. So if we set a seed to 100 or any other number, it'll make it so this is reproducible. And then we simulate from the model with a new event table, 100 subjects per study and 100 studies to try to get some information about the uncertainty in the model itself, using the uncertainty in the fixed effects parameters and the random effect parameters. You can see that you can look through each of these and see the values that are simulated and the solved values as well. More importantly, you can simply plot this to look at what's going on. You do plot sim and it'll give a ggplot object that you can modify and tweak the things that are in there, and allows you to do things like use xgx at the same time to add the scale log y10. So you can start here, see these values, and you can change it so you can see the steady state values on a semi-log plot. You can also do more complicated simulations with RxODE, but for right now, this is what we're looking at, and this is something that is useful in looking at the variability and the concentrations you should expect with TID dosing. So if we want to think about what we've covered xgxr, which allows the exploration of data sets, and it uses an R package, xgxr, for some helper functions, but it has this methodology and this idea that you have templates to be able to quickly do exploratory analysis in a standard way that's easy to validate. Next thing we have is once we've done this exploratory analysis, we can do a nonlinear mixed text model using nlmixr. And that nlmixr piece allows you to explore what these values would be and what the individual patients would be. If we want to go further, we can use ggPMX and use that ggPMX software to look at the goodness of fit plots and use information from that to assess how well we're doing at describing the data we have. Last piece is once we have this nlmixr model and we've assessed with ggPMX, we can use the functions from xgx and from RxODE to simulate a new dosing scenario. So since we can simulate that, we can answer questions about how things occur in the clinic. So we have end-to-end question from and answer from the very beginning where we have our data set to the very end where we have questions we're trying to answer with the data and the model. We can do it all in R and all using these open source software packages. If you ever want to find this, you can always go to the nlmixr website. So typically it's nlmixr.org. And then there you have this part where it has articles. It has integrated development with xgxr, nlmixr, and ggPMX. And it shows this example where you can go end to end from the beginning of a data set to the end where you're answering questions with RxODE, and it allows you to talk through the whole thing and see how it can work. Thank you for your time. If you have any questions about any piece of this software or packages or any of this that you'd like to have more information about, feel free to ask me or any of my co-team members, Allison or Suvik, and we'll be glad to answer any questions.